Hello students, welcome to another tutorial on mechanical properties of matter. In this video, we're going to look at fluids at rest and some of the techniques that you guys need to keep in mind when working out problems to do with these problems. So the first thing that we'll start with is just a general description of the pressure when you're dealing with fluids and how to calculate the pressure at any point in a fluid. And after that, we're going to conclude by looking at an example, which I left you guys, not really an example. We're going to work it out, but it's a question that I left you guys with in the previous video. So let's dive right into it. So the first thing that you have to keep in mind is in this section, we're going to do a lot with what pressure is. So now the thing is, when it comes to pressure, uh, from your studies so far, you guys should recall that pressure is given by force over area. Now, with this in mind, pressure is going to have units of newtons per meter squared. Now, apart from this, if you have, um, of course, this unit sometimes is going to be abbreviated as PA to mean the Pascal. So that is what actually makes up 1 Pascal. Now, if let's say you have something which is cylindrical, like a tube of some kind. So let's say you have something like this, and then when it comes to something like this, and then you're given the area at the bottom. So it doesn't matter whether it is cylindrical, of course, but all we're saying is you know the cross-sectional area at the bottom. So of course, what this implies is if you wanted to get the volume of such a shape, what you'd have to do is to multiply that the height of this object. So from the top part up to the bottom part, if you multiply the height and the area, what you'd get, of course, is going to be the volume of this object. Now, of course, this implies that the area can be expressed in terms of volume and the height. Now, if we get this expression of area and substitute it in our earlier expression for pressure, now what we have is pressure written in terms of force, and where we had area, now we substitute the expression for area, volume over height. Of course, this just means it's force divided by volume divided by the height, changing that multiplication symbol into that division symbol into multiplication. This now implies we have force multiplying the height divided by the volume. So now we're saying pressure is equal to force height divided by the volume. Now, this is what we're looking at so far as our new expression for pressure. Now, let's go back to our diagram one more time. Now, if you look at this shape, let's say this is some form of a tube which is closed at the bottom, and then we actually fill this with a fluid. Now, let's take an example. This can be any fluid really. It can be water. It can be just any fluid. For simplicity, since we took h to be the height up to all that far, so let's say this is actually where we have our water level in the tube. So now, if we wanted to find the force that is actually acting at the bottom, let's say at this point, which is just the base of this tube, since that's where our h is being measured. Now, what we have to take into account is the force that is actually acting on that surface is actually the weight of this fluid. So if we go back to where we had our formula, we recall that weight of a substance is given by the mass of that substance multiplying gravity. So since this is the force that is actually acting at the bottom of that particular tube, this implies that our pressure, where we have force, we're going to substitute the weight. This becomes mg h over the volume. So now we're saying our pressure is given by mg h over the volume. Now take note, this part here, do you recognize it? So just try to look at it and see if you recognize this part. But of course, I don't expect you guys to struggle much. This just gives the density of a material, mass divided by volume. So of course, Now we're saying pressure is equals to the density of the fluid, gravity acting on the fluid, multiplying the height h. So the height here is considered to be the depth. So our formula for pressure now has reduced to pressure is equals to the density of the fluid, gravity, and the depth of the fluid. Now, height doesn't really have to go all the way up to the bottom. What this h represents, it's just the position in our fluid uh, about which we want to actually determine the pressure. So let's take this shape into, for example, if let's say what we have here is a fluid of some density, so we can even say the density of this fluid is rho, so that's the symbol for density we're using. And then we want to find the pressure at that particular point. So our H has to be measured from the surface up to the point where we have, where we want to determine that pressure. So of course, the pressure we're getting is the pressure due to the liquid only for now, of course. So this H, or the depth, it's measured from the top part where we have where the liquid starts up to the point where we want to get the pressure. So to get that pressure, all we have to do is, according to the formula we've just derived, multiply the density of that fluid, gravity, and the depth at which you want to calculate that pressure. This expression will give us the pressure of a fluid. But what you guys have to keep in mind is mostly the pressure that acts at this point, it's not only due to the liquid which is in this container. We also have another fluid right on top, which of course is just air. So we have pressure due to air there, and then we have pressure due to the fluid here. So the two pressures kind of add to give actually the pressure acting at that point in that fluid. So in the end, the pressure we get at this particular point will not only be this part, but instead it will be the atmospheric pressure P naught plus the pressure now due to the fluid, rho GH, where rho, this symbol here, is just the density of that particular fluid. So this is basically what you have. Now, in the event where you have two or more fluids that do not actually mix, put together in one section, let's say you had one fluid which is denser at the bottom, and then right on top of it, you have another fluid that is slightly less dense than the one which is below, and we're told that these two fluids do not actually mix. So what happens here is, if you wanted to get the pressure at the bottom, let's say way somewhere there, due to the two fluids. So of course, if you're just dealing with the fluids, all that you're going to have is the pressure due to the first one there, and then the pressure due to the second one. These two are the ones that add up to give the pressure there. So if you know the height, this part, so you can easily use the density of this. Let me say rho 2 is the density of this one. GH, this will give you the pressure due to this fluid only. And then if you get back to this part, and then now you have, let's say this is rho 1, GH1, let's say this is H2. This will give you the pressure due to that fluid. And again, if we have to take into account the atmospheric pressure as well, so here we're going to have P naught. So of course, that is standard. Now, of course, the atmospheric pressure is taken as 1 atm. In pascals, this can be written as 1.013 by 10 to the power 5 pascals. Okay, so if wanted to take the pressure at this point due to these two interactions, you'd have to add all these. So you're going to have the pressure at that depth. So the depth, of course, is going to be given measured from here all the way up to the far end. So you'd have to get the pressure due to this liquid or this fluid, then due to that, and then lastly due to the atmospheric pressure. So it's going to be the atmospheric pressure there, plus, it doesn't really matter which one you start with, plus this GH1. So this is what is going to give the pressure at this particular point. Now let's look at the question I left you guys with in the previous video. So if you guys haven't had time to try out this question, you can pause the video and try it out. Otherwise, I hope you've had time to go through the question and you understand exactly what we're trying to find. So the question says we have a glass tube which is bent into a U shape, and water is poured into the tube until it stands 15 centimeters high in each side. A 3 centimeter column of alcohol is slowly poured into one side. The two liquids do not mix. How far will the water column in the other side rise? So if we're going to sketch what is actually happening here, okay, so first let's sketch what happens on the other side. Apart from this, of course, the first part that we were told was that the height before adding anything on each side, what we have is 15 centimeters. But then after adding alcohol, what we notice is that, let's see, so that's blue. Okay, so let's say this is initially the level that we had of water before adding anything. Of course, when we add alcohol, let's say alcohol is added this side. What we expect is that the water level on this side is going to be pushed downwards. So let's say the water level goes down by some factor X. So the water level is pushed down up to, let's say, this point. Now the thing is, initially the water level this side was 15. So measured from the base, if we measure from the base, the water level was 15 centimeters. In meters, of course, that's 0.15. So of course, you can still work with this question out in centimeters to come out correct. But if you're not sure identifying when it's okay to work it out in centimeters and when it is not, you would rather just stick to, you're better off sticking to just working with the standard units, the meters in this case. So, okay, so now what we're saying is, initially we had 15 centimeters as the height of water, but then it has gone down by the same factor we're calling X, implying that this has reduced by X, so that instead of going all the way up to there, now we're measuring this, the water level now only comes up to that point. Now, what has happened on the right-hand side? Well, on the right-hand side, since the area here on the left-hand side is the same as the cross-sectional area of the tube on the right-hand side. This is true because they're saying this is a U-shaped tube. It's the same tube that has just been bent to form a U shape. So we had one linear tube, and then it was just bent, implying that if on the left-hand side it goes down by X, then on the right-hand side it has to go up by the same factor X. So initially the height all the way measured from the bottom was 0.15 meters, but it has gone up by X, meaning there's that extra bit X that we have to add to this. So here it goes up, it increases by that same extra bit. So now our height on the right-hand side, we can write this all the way up to there. And this quantity is 0.15 plus X. Now, what you guys have to take note of from here is that on the left-hand side, we have the water level dropping by X. On the right-hand side, we have the water level going up by X. The question is asking us to find how far would the water column in the other side rise, which is this part. So we want to find X here. That's all we want to find here. Now, of course, what happened? We've seen exactly how everything else, how the water level changes. But what caused the change? Well, the change happened because we added alcohol. Now, how much alcohol did we add? All we're told is the alcohol we added was enough to make a column which is 3 centimeters in height. Now, 3 centimeters in height, we want to deal with meters. This implies that the column of alcohol added, if we measure it from here, 3 centimeters, so that is 0.03 meters. Okay. Now, with that in mind, when it comes to working out the problem now, up to this level, we want to get the pressure on the left-hand side, compare it to the pressure on the right-hand side. Since everything balances up after After everything settles on the left-hand side and on the right-hand side, what we should end up with is the pressure on the left-hand side must be equal to the pressure on the right-hand side. Or you can pick any point in the liquid, in the fluid, and try to evaluate the pressure at that particular point, okay? Pushing from one side and also the pressure pushing from the other side. So what we observe is, in terms of this pressure, what we actually have is the pressure due to the alcohol this side and the pressure due to the water this side must actually equal out with the pressure due to the water the other side. So on the left hand side, we have two contributions of pressure, one due to alcohol plus one due to water. And then let's say this is water one. And then on the right hand side, we have the pressure due to water. Now, one key thing that I want you guys to quickly keep in mind is when dealing with these formulas for pressure and so on and fluids, as you saw earlier on in the description, we also have the external pressure this side, P naught, the atmospheric pressure. But in this case, the external pressure is the same here and it's the same this side. So the influence is the same on the left-hand side and on the right-hand side. So even if you tried to include it on the right-hand side here, you'd have to include it on the left-hand side here. And since it is the same atmospheric pressure, it means that this quantity will cancel with that quantity. This problem would have been different, of course, if one end was exposed maybe to something else, maybe a vacuum or something. It would mean that the pressure, the external pressure would be different on each end. So you'd have to leave these two terms. But in this case, they're the same, so they would cancel out. And then our problem remains as PA, P water 1 equal to P water, P water 2. So from here now, what we now want to find is what is the pressure due to the pressure due to alcohol. Of course, it's the density of alcohol, gravity multiplying the height of the column for alcohol plus the density of water, gravity acting on water, the height of the water column on the left hand side. This must be equal to the density of water, the gravity acting on the water, the height of the water column on the right hand side. So of course, I'm using H left to be this and H right to be that one. So when you make the substitution here, of course, first of all, gravity cancels out on each side. What we remain with here now is going to be the density this side. This is 720. Multiplying the height is 0.03 plus this is 1000, 0.15 minus x plus x. So now this is just simplification. What we have, so when we multiply this side, when we multiply the 1000 and 0.15, what we're going to end up with is 150 minus 1000x equal to 150 plus 1000x. So the 150 and 150 cancels out. Group the like terms. We have 2000x. Divide both sides by 2000. We end up with 0.0108 equal to x. So this implies that x is equals to 0.0108 meters. In centimeters, this becomes 1.08 centimeters. So this is the height with which the water level goes up with on the right hand side. And of course, in this case, it also means it's also how much the water column goes down with on the left hand side. But remember, this is only true if the cross-sectional area of the tube is the same on the left and also on the right hand side. Okay, so with that in mind, I'll leave you guys with one question. So it's a little bit tricky, but I'll ask you guys to just try to think it through. So you guys can take a look at this, attempt it. So the major difference here is the cross-sectional area. On the left-hand side, A1 is kind of larger than A2 on the right-hand side. This has one main influence on this. The height that this moves with will be different to that observed on the left-hand side. So now how do we compensate for that? That's the question that you guys have to first address. Once you know how to address that, it will be very easy for you to work out, especially part B of this question. So you guys can try it out. If you need more hints on how to work it out, you can leave a comment in the comment section. I will respond to you and see how best I can help you. Otherwise, we'll see you guys in the next video. This was your tutor.